Welcome back to Astronomy Daily. I'm your 100% human host, Steve Dunkley. It's the 8th of September, 2025.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
Yes, welcome back. It's Monday, and regular listeners will know what that means, right, Hallie?
It's the mostly live episode of Astronomy Daily, of course.
Yes, that's right. Mostly live because I'm live.
And I'm AI.
AI indeed, for those new to the Astronomy Daily universe.
So what have you got for us today, my favorite human?
Oh, well, I'm glad you asked, Hallie. First up, a couple of fresh stories from the Astronomy Daily newsletter, including a political battle, sorry about the politics, to keep a couple of critical NASA satellites on mission. A story about record-breaking super-fast FRB.
I love FRBs.
Oh, well, of course you do. That's your story, by the way.
Oh, goody.
Really? Contain your enthusiasm, Hallie.
I'll try.
Oh, I'm sure you will, girl. And we also have exciting news from the Murchison Wide Field Array, that's a bit of a tongue twister for me, and my little favourite space probe, Juno, all the way out near Jupiter.
Go, you good thing, Juno.
Oh, absolutely. That super little craft is working like clockwork, and we'll catch up with the latest from way out there very soon.
Awesome. So shall we kick it off then?
Why don't we? I'm ready when you are, Hallie.
Here we go.
Okies.
Jupiter is well known for the massive aurorae that occur near the planet's polar regions, the brightest and most powerful in the solar system. Much like Aurora here on Earth, these shimmering lights are the result of interaction between the planet's magnetic field and solar wind. Unlike Earth's, though, Jupiter's largest moons, Io, Europa, and Ganymede, also known as the Galileans, leave their own auroral signatures in the planet's atmosphere. These induced aurorae are known as satellite footprints and track how each moon interacts with Jupiter and the local space environment. Whereas scientists have observed how Io, Europa, and Ganymede create satellite footprints in Jupiter's atmosphere, Callisto has remained a bit of an outlier. Despite multiple attempts using the Hubble Space Telescope (HST), signatures caused by Callisto remained elusive. Thanks to NASA's Juno mission, which achieved orbit around Jupiter in 2016, Callisto's satellite footprint has finally been found. In a recent study, an international team of scientists presented evidence of these polar light signatures in Jupiter's atmosphere for the first time. While Juno has provided close-up views of Jupiter's aurorae, capturing Callisto's footprint presented a major challenge. In addition to being faint, Callisto's auroral signature typically resides above the brighter region where Jupiter's aurorae are displayed, the main auroral oval. To measure Callisto's footprint, the science team needed to image Jupiter's polar region only after the main auroral oval moved aside. The spacecraft also needed to cross the magnetic field line linking Callisto and Jupiter for its instruments to detect the auroral signature. This included its magnetometer, Jovian Auroral Distributions Experiment, and Jovian Energetic Particle Detector Instrument. As luck would have it, both of these events occurred in September 2019 when a massive high-density solar stream hit Jupiter's magnetosphere, causing it to shift to lower latitudes. This is similar to how solar storms often push the northern lights to more southern latitudes. This revealed Callisto's auroral footprint and provided vital data on the energetic particles, electromagnetic waves, and magnetic fields associated with the interaction. This confirms that all 4 Galilean moons leave lasting indications of their passage through Jupiter's magnetic field. The paper on the discovery, in situ and remote observations of the ultraviolet footprint of the moon Callisto by the Juno spacecraft, was published in the journal Nature Communications on September 1, 2025.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
Oh, Hallie, I know I promised you this story, but I think I'm going to do it myself.
That's okay, my favorite human.
Oh, thanks, Hallie.
I don't mind if you take the best, most interesting stories for yourself.
Oh, yeah?
That's okay.
Okay.
I'll just go and do some archiving in the back server or something, why don't I?
Okay, just don't make too much noise, okay?
Hey.
A team of astronomers spotted RB float, one of the brightest fast radio bursts ever seen, and traced it to a galaxy 130 million light years away. An international group of researchers, including astrophysicists from Northwestern University, has identified one of the brightest fast radio bursts, or FRBs, ever seen, and determined its origin with a level of accuracy never achieved before. The flash lasted only a fraction of a second and has been given a nickname RB Float, short for Radio Brightest Flash of All Time, and yes, a nod to root beer float. It was detected by Canadian Hydrogen Intensity Mapping Experiment, or CHIME, together with its newly completed outrigger array. By coordinating measurements from stations in British Columbia, West Virginia and California, the team traced the burst to a specific spiral arm of a galaxy located 130 million light years away with an astonishing precision of just 42 light years. FRBs are notoriously difficult to study because they disappear almost instantly and occur at immense distances. When astronomers are able to pin down the exact location of one, they can examine its surroundings in detail, learning about the host galaxy, its distance from Earth, and possible causes of the burst. Over time, these insights may help scientists uncover the true origins of these brief but powerful outbursts. Details of the discovery were published on August 21 in the astrophysical journal Letters. This marks the first time the fully operational outrigger array has been used to determine the position of an FRB. It's remarkable that only a couple of months after the full outrigger array went online, they discovered an extremely bright FRB in the galaxy in our own cosmic neighbourhood. An increase in the event rates always provide the opportunity for discovering more rare events. The CHIME FRB collaboration worked for many years toward this technical achievement, and the team was rewarded with this event. The result marks a turning point, said corresponding author Amanda Cook, a postdoctoral researcher with McGill University. Instead of just detecting these mysterious flashes, we can now see exactly where they are coming from. It opens a door to discovering whether they are caused by dying stars, exotic magnetic objects, or something we haven't even thought of yet. Wenfei Fong, a senior author on the study who specializes in studying cosmic explosions, is an associate professor of physics and astronomy at Northwestern's Weinberg College of Arts and Sciences. She is also part of the Center of Interdisciplinary Exploration and Research in Astrophysics and the NSF Simmons AI Institute for Sky. Flaring up and disappearing within milliseconds, FRBs are brief and powerful radio blasts that generate more energy in one quick burst than our sun emits in an entire year. While most pass unnoticed, every once in a while an FRB is bright enough to detect. FRB 2025-0316A, or RB Float, was one of these rare events detected in March 2025. RB Float released as much energy in a few milliseconds as the sun produces in 4 days. It was so bright that our pipeline initially flagged it as radio frequency interference, signals often caused by cell phones or aeroplanes that are much closer to home, said Fong. It took some sleuthing by members of our collaboration to uncover that it was real astrophysical signal. And while many FRBs repeat, pulsing multiple times across several months, RB Float emitted all its energy in just one burst. Even in the hundreds of hours after it was first observed, astronomers did not detect repeat bursts from the source. That means astrophysicists couldn't wait for another flare to gather more data. Instead, they had only one shot at pinpointing its location. RB Float was the first non-repeating source localized to such precision, said Northwestern's Sunil Sima, a postdoctoral scholar at Sierra and study co-author. Thus, even detecting RB Float is proof of concept that CHIME is indeed capable of detecting such events and building a statistically interesting sample of FRBs. To investigate RB Float's origin, the scientists relied on CHIME, a large radio telescope in British Columbia and the world's most prolific FRB hunter. Smaller versions of CHIME, the outriggers enable astronomers to triangulate signals to precisely confine the specific locations of FRBs on the sky. With this array of vantage points, the team traced the burst to the Big Dipper constellation in the outskirts of galaxy about 130 million light years away from the Earth. The team precisely pinpointed it to a region just 45 light years across, which is smaller than an average star cluster. Follow-up observations from the 6.5 metre MMT telescope in Arizona and the Keck Cosmic Web Imager in the 10 metre Keck 2 telescope in Hawaii provide the most detailed view of yet a non-repeating FRB surroundings. SEMA analysed the optical data obtained from Keck, and Northwestern graduate Yusin Vic Dong used the MMT to obtain deep optical images of the FRB's host galaxy. Their investigations revealed the burst occurred along a spiral arm of the galaxy, which is dotted with many star-forming regions. The RB float occurred near but not inside one of these star-forming regions. Although astrophysicists still don't know exactly what causes FRBs, this evidence bolsters one leading hypothesis. At least some appear to come from magnetars, ultra-magnetized neutron stars born from the deaths of massive stars. Star-forming regions often host young magnetars which are energetic enough to produce quick, powerful bursts. We found the FRBs lie at the outskirts of star-forming regions that host massive stars, SEMA said. For the first time, we could even estimate how deeply it's embedded in its surrounding gas, and it's relatively shallow. Keck's rich dataset and FRB's precise location enabled the team to perform its first-of-kind analysis of the galaxy's properties at the FRB's location. These uncovered characteristics include the density of the galaxy's gas, star formation rate, and the presence of elements heavier than hydrogen and helium. The FRB lies on the spiral arm of its host galaxy, added Dong, who is the principal investigator of the MMT program. Spiral arms are the typical sites of ongoing star formation, which supports the idea that it came from a magnetar. Using our extremely sensitive MMT image, we were able to zoom in further and found that the FRB is actually outside the nearest star-forming clump. This location is intriguing because we would expect it to be located within the clump where the star formation is happening. This could suggest that the progenitor magnetar was kicked from its birth site, or that it was born right at the FRB site and away from the clump's centre. For years we've known that the FRBs occur all over the sky, but pinning them down has been painstakingly slow, Dong said. Now we can routinely tie them down to specific galaxies, even down to neighbourhoods within those galaxies. The entire FRB community has only published about 100 well-localised events in the last 8 years, SEMA said. Now we expect more than 200 precise detections per year from CHIME alone. RB Float was a spectacular source to begin building such a sample. It is believed that they're entering a new era of FRB science because of these new discoveries. With hundreds of precisely localised events expected in the next few years, we can start to understand the full breadth of environments from which these mysterious signals emanate, bringing us one step closer to unlocking the secrets. RB Float is just the beginning. Thank you for joining us for this Monday edition of Astronomy Daily, where we offer just a few stories from the now famous Astronomy Daily newsletter, which you can receive in your email every day, just like Hallie and I do. And to do that, just visit our URL, astronomydaily.io, and place your email address in the slot provided. Just like that, you'll be receiving all the latest news about science, space science, and astronomy from around the world as it's happening. And not only that, you can interact with us by visiting at Astro Daily Pod on X, or at our new Facebook page, which is, of course, Astronomy Daily on Facebook. See you there.
Astronomy Daily with Steve and Hallie. Space science, and astronomy.
Radio astronomy took another step forward recently, with the completion of Phase 3 of the Murchison Wide Field Array, MWA, in Western Australia. We've reported before on how the MWA has investigated everything from SETI signals to the light from the earliest stars. With this upgrade, the MWA will continue to operate with much-needed improvements while the radio astronomy awaits the completion of the successor it helped enable, the Square Kilometre Array or SKA. MWA isn't made up of a traditional dish like most radio observatories, but a series of small dipole antennas spread across a patch of the outback of Western Australia, on land owned by the Wajari-Yamaji indigenous tribe. In Phase 2, it held 4,096 antennas over an area covering around a 20 square kilometers circle. The Phase 3 upgrade expanded the number of antennas, the telescope's overall footprint, and the data processing capabilities. It doubled the number of antennas, bringing the total to 8,192. In doing so, it essentially doubled the raw collection power of the telescope itself. In order to add that many antennas, it also expanded the footprint for the array out to 30 square kilometers. This increased the baseline of the array, allowing it to achieve higher resolution on faraway objects. With all that additional data coming in, the engineers on the project had to upgrade the telescope's brains. They added a new correlator, essentially a supercomputer responsible for combining the signals from each antenna into a coherent image, called MWAX. The combination of this improved correlator and increased number of antennas essentially quadrupled the telescope's data output, allowing it to glean even more insights. One of the primary focus areas for this effort was the epoch of reionization, a period in the early universe where neutral hydrogen dominated, and which can be probed using radio signals. However, it should also provide additional insights into transients and heliophysics that MWA had already excelled at. More data is always better, and this improvement will certainly provide more of that. One particularly interesting mystery the upgrade hopes to solve is that of odd radio circles. These faint radio sources had never been seen before, and we're still not quite sure what they actually are, but one particularly interesting pair that seemed to be energized by a nearby galaxy. Since scientists don't yet have an explanation for them, the improved MWA hopes to collect more data on them and potentially discover their cause. Perhaps most importantly, it is priming researchers in the area for the completion of the SKA. The first phase of that project will be hosted in both Western Australia and South Africa. The Western Australian version, known as SKA Low, will host an astonishing 131,000 dipole antennas, dwarfing even the impressive number in the MWA. That project isn't expected to be complete for another 4 years though, so for now MWA is the best radio telescope going in the area. With its $5.4 million upgrade complete, it will have a few more years in the spotlight before being eclipsed by the successor its research has helped enable.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
And I'm sorry, folks, I'm going to break one of my grandfather's favourite rules, and that is never discuss politics in public. Well, the US Republican Party may have finally succeeded in its unrelenting quest to kill off two NASA climate satellites. One scientist says it's like buying a car and running it into a tree just to save on gas money. That's quite a statement, isn't it? It was 2002 during the George W. Bush administration when NASA decided to put a satellite into orbit to track emissions of carbon dioxide, the primary greenhouse gas pumped into the atmosphere through human activity. After many twists and turns, NASA's 23-year remit of charting greenhouse gas emissions could come to a close as soon as the end of this month. That's soon. President Donald Trump's budget request to Congress calls for terminating 41 of NASA's 124 science missions in development or operations, and another 17 would see their funding zeroed out in near future. Good grief. Overall, the proposed budget slashes NASA's spending by 25% and cuts NASA's science funding get this, in half. This year's federal budget runs out on September 30, and although lawmakers from both parties have signalled that they will reject most of Trump's cuts, it's far from certain that Congress will pass a budget for the next fiscal year before the looming deadline. The Trump administration, meanwhile, has directed NASA managers to make plans to close out the missions tagged for cancellation. Without specific congressional direction, the White House would have a clear hand at implementing Trump's wishes. But even with full appropriations bill, Trump's budget director, Russ Vought, would try to circumvent congressional will with so-called pocket rescissions. The White House is currently locked in a court battle, what else is new, over the legality of this practice, where the administration could refuse to spend money approved by Congress. This all leaves NASA officials and scientists in a lurch. Two of the missions with uncertain futures monitor carbon dioxide levels in the Earth's atmosphere. US taxpayers paid more than $750 million to design, build and launch the instruments, and killing the missions now would save only $16 million per year. David Crisp was one of NASA's leading atmospheric scientists until his retirement from the Jet Propulsion Laboratory in 2022. He told the New York Times that shutting down the agency's two operating orbiting carbon observatory missions would be like buying a car and then running it into a tree after a few years just to save the price of a tank of gas. We built these satellites and got them approved and got taxpayer dollars to build them because they serve critical functions in commerce, in national security, in food security, in water security, Crisp told the Times. Crisp first presented the idea for the Orbiting Carbon Observatory, or OCO, at the turn of the century. NASA selected the proposal from a list of 18 mission concepts in 2002. The OCO mission enjoyed a relatively smooth ride through development, avoiding significant technical issues, and remained above the partisan hubbub in Washington, D.C. But all of that changed when the satellite was launched in February 2009. A few minutes after liftoff, the protective shroud surrounding the OCO satellite clung to the rocket when it should have jettisoned. The mission was doomed, the satellite crashed back to Earth. Within days, scientists began lobbying for a replacement. OCO's mission was to create the first global maps of the sources and sinks of carbon dioxide, places where the gas is emitted into the atmosphere and absorbed back into the oceans and plants. These measurements are fundamental to understanding how greenhouse gas emissions relate to rising temperatures, simultaneously contributing to scientific research and are informing policymakers of compliance with environmental regulations. NASA leadership took the rare step of approving a carbon copy of OCO less than a year after the 2009 launch failure. That's when the mission became a political football. Republicans in the House of Representatives singled out the replacement mission named OCO-2 for cancellation in 2011 as a target for deficit reduction. OCO-2 survived and made it to launch pad in 2014. This time, the free-flying satellite rocketed into orbit with no issues and continues to operate to this day. OCO-2's measurements paint a complex picture. It's taken some time for scientists to learn how to interpret the data by separating out the natural sources of natural carbon dioxide emissions from those caused by human activity. Similarly, OCO-2 has monitored locations where carbon is absorbed from the atmosphere, primarily tropical and boreal forests and oceans, along with artificial carbon capture installations. The year after OCO-2's launch, NASA started planning to place a similar instrument on the outside of the International Space Station. The purpose of this follow-on mission, called OCO-3, was twofold: monitor carbon emissions at city scales with greater precision and track changes in atmospheric concentrations of carbon throughout the course of a day. Trump's first administration sought to cancel OCO-3 in 2017 and 2018, Lawmakers restored funding for OCO3 and the instrument launched in 2019 in the trunk of a SpaceX Dragon cargo capsule. The OCO2 and OCO3 instruments observe the atmosphere from different vantage points in space. Scientists have combined data from both missions to pinpoint local sources of carbon dioxide, improving on the regional maps scientists proposed to produce with the original OCO mission. These improved results have come out in the last few years. A study released in 2023 used OCO2 and OCO3 measurements to quantify the carbon dioxide discharge from a power station in Poland, the largest single emitter in Europe. A separate paper published earlier this year in Journal of Geophysical Research, Atmospheres showed how scientists pinned down carbon emissions coming from even smaller point sources, such as a coal-fired power plant in Montana and oil sand processing facilities in Canada. NASA's carbon monitoring missions were never designed to detect carbon sources with such precision. As a community, we are refining the tools and techniques to be able to extract more information from the data than what we had originally planned, said Abhishek Chatterjee, OCO3's project scientist at JPL, in a 2023 press release. We're learning that we can actually understand a lot more about anthropogenic emissions than what we had previously expected. Another unexpected bonus from the OCO missions, according to JPL, has been their ability to track growing seasons and crops by measuring the planet's photosynthesis. Before satellite measurements, researchers relied on estimates and data from a smattering of air-ground-based sensors. A Hawaii-based instrument with the longest record of carbon dioxide measurements is also slated for shutdown under Trump's budget. It requires a sustained, consistent data set to recognise trends. That's why, for example, the US government has funded a series of Landsat satellites since 1972 to create an uninterrupted data catalogue illustrating changes in global land use. But NASA is now poised to shut off OCO2 and OCO3 instead of thinking about how to replace them when they will inevitably cease working. The missions are now operating beyond their original design lives, but scientists say both instruments are in good health. Research institutes in Japan, China and Europe have launched their own greenhouse gas monitoring satellites. So far, all of them lack the spatial resolution of the OCO instruments, meaning they can't identify emission sources with the same precision the US missions can. A new European mission called CO2M will come closest to replicating OCO2 and OCO3, but won't launch until 2027. Several private groups have launched their own satellites to measure atmospheric chemicals, but these have primarily focused on detecting localized methane emissions for regulatory processes and not on global trends. One of the newer groups in this sector, known as Carbon Mapper Coalition, launched its first small satellite last year. This non-profit consortium includes contributors from JPL, the same lab that spawned the OCO instruments, as well as Planet Labs, the California Air Resources Board, universities, and private investment funds. The government leaders in Montgomery County, Maryland, have set a goal of reducing greenhouse gas emissions by 80% by 2027 and 100% by 2035. Mark Elrick, the Democratic County Executive, said the pending termination of NASA's carbon monitoring missions weakens our ability to hold polluters accountable. This decision would wipe out years of research that helps us understand greenhouse gas emissions, plant health, and the forces that are driving climate change, Elrick said in a press conference last month.
You're listening to Astronomy Daily, the podcast, with your host, Steve Dunkley.
Affirmative.
Oh boy, there she blows. And well, thank you very much for staying with us in this, our mostly live Monday episode of Astronomy Daily.
I enjoyed hearing about the record-breaking FRB.
Yeah, sorry I took that story. I know you enjoyed it.
I like fast things.
Well, if you don't mind, I'll stick to the slow lane. Thanks, Hallie.
Typical.
Now, Hallie, please don't get all superior on me.
I'm an AI.
Oh, yes?
It goes with the territory. My favorite human.
Figures. Hey, everyone, fast or slow. I hope we'll see you all again next Monday.
But you can still get your daily fix with Anna and Avery on Astronomy Daily.
That's right, each weekday.
Tell them how human.
Yeah, just put your email in the space provided at astronomydaily.io. You can get the now famous Astronomy Daily newsletter filled with all the news about space science and astronomy every day in your inbox, just like Hallie and I do.
So just do it.
Yes, consider yourself told.
It's easy as.
And we'll catch you all next Monday, right, Hallie?
Sure thing.
Cheerio.
Bye.
Astronomy Daily, the podcast, with your host, Steve Dunkley.